right, so we've established how to find the potential difference, which we often will call the EMF, for a metal bar that's moving through a region of constant magnetic field. So now what I want to do is to end up considering what happens whenever I connect this to other stuff. And what I'm going to connect it to, I'm going to have, there we go, I'm going to have a resistor, and then I'll have two metal rods here. These are stationary. I'm going to end up having this to end up moving to the right along that those two metal rods. So this is of course the conductor, and I'm going to end up having this to slide that direction at constant velocity. So, and in terms of terminology, remember we said the length from here to there, the end from the metal rod, was going to end up being L, and I'm going to end up calling this distance here from this end to that location, I'm going to call that W, for reasons that will end up becoming clear later. So if I end up calling that distance W, notice that my velocity in this direction is the rate of change that W is increasing. So my velocity in this situation is equal to the first derivative of W. So as I end up doing that, I end up having a, that will end up describing how this this scenario will work. So remember we said that the positive charge in this scenario was on this side, the negative charge was on that side. So what will happen then is that current will end up going, of course, from the positive side to the negative side. So the current will end up going around like that. And so in this situation, notice again with the bar being there, that it's going to end up going in this sense. And notice by my right-hand rule, if it's going around that way, notice that the direction of this is coming this way. But the direction of the magnetic field is that way, the opposite. So because that's true, I end up describing describe the current, first of all, as going around this way, but the current is in the opposite sense of the way the number of field lines is increasing, which we're going to come back to in a little bit. So, so that's describing why that's the case, and you can end up seeing where I drew in the current on your notes. All right, so the reason why we picked W instead of some other letter to end up representing that distance is because now if we look at that shape, the enclosed shape, where I put this here, that enclosed shape is a rectangle, right? So, and if this distance from here to here, sorry, it's backwards on a video camera, from here to there, if that distance is W, and the distance top to bottom is going to be L, then this will be length times width is going to end up being in descriptive of what's going on. First derivative of W with respect to time is my velocity. My length is L. So my EMF, then, as the notes end up saying, your velocity is dW dt. And so we end up with the first derivative of W times B times L times the sine of the angle between the velocity and the magnetic field. Notice in this situation, by assumption, my magnetic field is constant. We didn't talk about a changing magnetic field or anything like that, so the magnetic field is constant. And my length is also constant. It didn't change how long this was. And I didn't change the angle between the velocity and the magnetic field. So the magnetic field was constant not only in magnitude but also in direction. So if all of that's true, I can end up factoring in all of those other numbers into the derivative as I end up showing you on there. So your EMF then would be first derivative of your magnetic field times LW, the sine of your angle, and of course length times width is area. So so in that situation, then we have a vector vector magnitude times the magnitude of an area with a trig function. In order, so the sine doesn't look right. with that, in terms of figuring out what will happen, notice if my velocity, let's say, is going this way, my magnetic field, if we rotate it around, my magnetic field is going in that direction, then my area, because I've rotated it around, so this is now my plane, my area vector, if I measure it with respect to the way the current is going around, my area vector is going to be pointing this way. So the angle between here, and this one, is going to be 90 degrees plus this other angle over here. So it's going to end up, in terms of the angle between your magnetic field and the area vector, it will still be the sine of that, but it'll be the sine of 90 degrees plus your angle between V and B. And using a trig identity, the sine of 90 degrees plus an angle is equal to the negative of the cosine. And the cosine should start to sound familiar. So now I've got a magnetic field, vector space field, magnitude times the magnitude of an area, times the cosine of the angle between them, right? So that should sound really familiar by now. And that will end up being the dot product of your magnetic field with your area. And that this was with the assumption your magnetic field was constant. We'll worry about, and we'll have situations where we need it not to be. So the way that we generalize that, just like it was if we've got a constant electric field, if you remember way back when, we would end up talking about the electric flux. That would be your magnitude of your electric field times the area. Would be a dot product. And then to generalize that, we end up taking the integral of the field dotted with a differential area, and we'll do the same thing. So we now have your electric field, your EMF, is going to be minus your first derivative then of your magnetic flux. And that is called Faraday's law of induction. All right, so, and it is important to notice there is a minus sign in that formula. Your EMF is minus the first derivative. The minus sign ends up coming from the fact that your EMF direction is opposed to the way your magnetic field lines are changing. And Lenz's law, we're going to talk about in a minute, ends up going into that in more detail. We'll first step back and look at, since this is a new thing, we'll talk about the units for magnetic flux. Unlike the case for electric flux just has whatever units you have to stick together in order to make it work. So it was like voltmeters and Newton meters squared per coulomb. Magnetic flux, though, ends up having a special name. So it will be a volt second from the formula we have now. It's equal to a Tesla meter squared per second, which should be obvious from just the units that go together with it. But that has a special name too. It's called a Weber. So the unit for that has a special name. We're not going to do a whole lot with it, but if you end up seeing that symbol, Weber, that's what it's talking about. That's the unit for magnetic flux. All right, so the next thing we need to do past this. So we'll now consider Lenz's law. And let's see. In order to understand how Lenz's law will work, we will, Okay, so what we're going to think about here, we'll have a region on this side where there's no magnetic field at all. We'll have a dotted line where it will suddenly change over to have a constant magnetic field in the middle, then another dotted line where it will suddenly change over to no magnetic field over here. That's not very physical, but it's to end up helping you to understand what happens, which will be of importance. So let's suppose this object is just a ring of metal. So if this is a ring of metal, and we end up starting to move it across here, whenever it's over here, there's no magnetic field lines. So there's no magnetic field, no magnetic flux at all while it's over here. So the magnetic flux change is 0. So it's not changing as I come across here. As I keep moving, when I cross this barrier, something else happens. Because if I cross the barrier and I keep moving, now if I stop, I'm not changing it. If I keep moving, notice now I'm generating extra magnetic field lines that are going into the paper I'm holding. So in that scenario, I've got extra field lines going in this direction. So what will happen is, by changing the number of field lines this way, I will induce a current, but the current I will get is not the direction it's changing, it's the opposite of the direction it's changing. So the direction it's changing is coming in this direction. So as my loop moves here, my current will end up starting to set up, going around, coming outward rather than coming inward to here. The reason that and notice what that will end up doing. So if I end up having a current that goes around this way, the current itself causes a magnetic field, right? From what we talked about before the break. It's been a while, but before the break we talked about that. So that the current going around will induce a magnetic field that's going in the opposite direction. So what's happening here is that you're inducing, again, induction, you're inducing a current that tries to fight the change in the magnetic field. It never wins. So it's always fighting but never winning. So it eventually will end up still changing over, but it causes a current while that's happening. Now notice if I'm moving here in between, I have magnetic field lines in between, but if it's constant magnetic field, I'm not changing the number. Remember, it's the first derivative. It's not the number of field lines divided by time. It's the change in the field lines divided by time. So if the number of field lines don't change, it makes no difference how much magnetic field you've got. But as long as the number of field lines stays the same, you do not induce any current. But as you keep moving over here, now you end up coming to a region where you're losing lines that are going in. So that's equivalent in those regions where it's changing, that I'm generating extra ones coming that way, coming out. And in that situation, I induce a current that comes around the other way. And whenever that's happening, I'm adding this way. So I'm adding extra lines that end up trying to regain the field lines that we're going through. Again, it tries to fight a change. It tries to fight a change that it gains. It tries to fight a change when it loses. It never wins. It only fights. So it's not able to end up causing it to change. But this fact that the current that's developed inside there will end up being in a direction that's opposite of the way that the number of field lines is changing is called Lenz's law. And that ends up concluding this piece.